Now we will start our analysis with a simple line, a short circuit line. It's in most of the cases just they will take the letter S and C to represent a short circuit line, that will be taken as SC line. Remember that point. Now what is a short circuit line? We are considering a transmission line. Let us take this is the transmission line that what we have. Yet the load, it was completely shorted. That is, the load was shorted for a transmission line is said to be a short circuit line. So what is the impedance if we are shorting a line? The impedance is obviously 0. So instead of ZL, just we are supposed to take 0. So if ZL is equals to 0, how the parameters what we observed will be modified? That we observed 3 different parameters, input impedance. One by one I will take those 3. Zin is equals to, what is the basic equation of Zin? Z0 ZL plus ZZ0 tan beta L divided by Z0 plus ZZL tan beta L. This is for a lossless line, and initially I forgot to give you that assume that this is a lossless line. If this is lossless line, then only this equation is applicable. Now, as I said, the output of our transmission line, that is nothing but the load, was short circuited. Whenever it is short circuited, ZL is equals to 0. Substitute ZL is equals to 0 here. If you substitute ZL equals to 0, what you will get? Simply Z0 multiplied with 0, and this will be 0. Z0 will be cancelled. J tan beta L. If you rearrange this one, this will become JZ0 tan beta L. Z0 is a pure real term, tan beta L is a real term. So the quantity what we are getting is clearly it's a reactive term, right? Whenever we are considering a short circuit transmission line, you are getting a reactive, that's a clearly input impedance. At the input, a reactance will be there, pure reactance will be there. Now what is the type of that reactance? Capacitive reactance or inductive reactance? We don't know. That is purely dependent upon this electrical length beta L, because the positive or negative sign for this particular quantity is depend upon this beta L. This is also called as electrical length of the transmission line. L is physical length and beta into L is called as electrical length of the transmission line. So by taking appropriate for this one, appropriate value for this one, you can make this transmission line as capacitive load or inductive load. You can observe that particular phenomena. That is, once again clearly remember, depend upon beta L, right? Similarly, I will observe the second parameter gamma. Gamma is equals to, what is the basic equation for gamma? ZL minus Z0 divided by ZL plus Z0. As I said, ZL is equals to 0 for a short circuit line. What you will get is minus Z0 divided by plus Z0, which is equals to minus 1, right? Gamma equals to minus 1. Just I want a little analysis for this particular gamma. How you define this gamma? Gamma is the ratio of the voltage which is traveling in opposite direction to the voltage which is traveling in positive direction. So simply I will take this one as V which is reflected divided by V which is incident. Then if you take this relation, what you will get is V reflected is equals to minus of V incident. What you can understand? The voltage magnitudes are same. How much amount of voltage I am applying, the same amount of voltage I am observing when it is reflected. That is 100% of our voltage was reflected from the load. Nothing is transmitted to the load. So nothing was transmitted to the space, or nothing was transmitted to the next section what we are connecting if it is short circuited. The entire voltage will be completely reflected with out of phase. Right? Clearly the incident voltage and reflected voltage are out of phase. So the entire signal will be cancelled in this particular region. As they are out of phase, it's a 180 degrees phase difference is there. Therefore, there will be no actual signal here. Right? This is our simple analysis with the help of this gamma minus 1. Similarly, third parameter, yes, I am observing. That is 1 plus magnitude of gamma divided by 1 minus magnitude of gamma. So if you substitute gamma here, gamma is minus 1. It's a 1 plus 1 divided by 1 minus 1. What you will get is an infinite. that the maximum voltage standing wave ratio will be there. So you are observing the entire reflected signal and the incident signal within that particular transmission line only. So the voltage standing wave ratio will be the maximum for this one. So this is a very simple analysis you are supposed to remember. So whenever the particular transmission line is short circuited, the input impedance is a pure reactance. Clearly remember, there is no resistance and there is no, that's a real part here, it is only imaginary part, that's a pure reactance. This reactance is also depend upon beta L, electrical length of the transmission line. So based on that one only we are supposed to define or decide that is a capacitive or inductive load. And then reflection coefficient is the maximum. Since it is maximum, you can say that the entire amount of voltage was reflected. The standing wave ratio is also maximum. So this is a simple analysis for our one of the transmission lines. Next we will move to our open circuit line. Now we will observe what is open circuit line. It's as I said for our previous case, here also open circuit will be taken as OC. In some of the papers or question papers or examinations, they will take this one as ZOC, right? So open circuit line always will be opened. Let us take a transmission line is there. Once again assume that the transmission line is a lossless line. For that lossless line, the output was not at all connected to anything. That it was completely opened. Whenever it is opened, what is the input? What is the impedance at that particular point? ZL is approximately equals to infinite. So highest amount of load impedance will be there, right? If it is open, ZL is equals to infinity is the condition that what you are supposed to remember. With this condition, we will try to modify our input impedance, reflection coefficient and standing wave ratio again, right? Consider the input impedance. Zin is equals to, what is the equation? Z0, ZL plus JZ0 tan beta L. As it is a lossless line, I am taking this equation. Z0 plus JZL tan beta L. Now substitute this ZL is equals to infinite here, but so this is undefined. Directly substitute, direct substitution is not at all possible. So apply limit ZL tends to infinity and simplify this one. For this one, which is equals to Z0, if you take this ZL common, 1 plus JZ0 divided by ZL tan beta L, here you will get divided by, here it is Z0 by ZL plus J tan beta L. Now apply ZL tends to infinity. If you are applying ZL tends to infinity, this term and this term will be vanished. These two will become 0, right? If these two will become 0, the term which is remained for us is simply Z0 divided by J tan beta L. Z0 divided by J tan beta L is nothing but minus JZ0 cot beta L. Directly I am writing this one here, minus JZ0 cot beta L. This is the input impedance of an open circuit line. Clearly once again observe, for an open circuit line the input impedance is once again pure reactance. There is no real term here, only imaginary part is there. That's why you can take the open circuit line as an imaginary impedance provider, right? So what is the type of impedance here? Once again, that is purely dependent upon this beta L. That purely depending on the electrical length only, the input impedance type will be decided, whether it is capacitive or inductive will be decided purely dependent upon the electrical length of the transmission line. Here I will give a simple notation to this as ZOC. You can take the previous notation, or in the previous case you can take the notation as ZSC. Here I am taking the notation as ZOC, right? Z open circuit is equals to minus JZ0 cot beta L, that is the input impedance. Similarly, the second parameter I am going to observe, that is reflection coefficient gamma. Gamma is equals to ZL minus Z0 divided by ZL plus Z0. Now take ZL common from this one. So what you will get is 1 minus Z0 by ZL divided by 1 plus Z0 by ZL. So as ZL tends to infinity, 1 by 1 you will get just it is 1. 1 means, go to the previous analysis and recollect what we did, which is equals to V reflected divided by V incident. So V reflected is equals to V incident corresponds to the voltage which is reflected from the transmission line end is equals to the incident voltage. That is the complete voltage was reflected even without phase shift. So whatever the signal we are applying to a transmission line, it's not at all going to the next section again. It's not at all going to the antenna. It is not at all going to the free space. Directly that stops there and reflects without any phase shift. So once again you can observe the voltage standing wave and the maximum voltage standing wave ratio will be there. That we will observe now. For that, calculate S also. S is equals to 1 plus magnitude of gamma divided by 1 minus magnitude of gamma. As gamma is equals to 1, you can directly take this one as 1 plus 1 divided by 1 minus 1 will gives you infinite. So the maximum voltage standing wave ratio you can observe for this case also. So these two cases will gives you a zero propagation, that what I can say. So whenever the signal is applied and the output is short circuited, the signal is applied, the output is open circuited. In these two cases, from the output you are not getting anything. That the complete signal will be reflected with phase shift or without phase shift, that's purely depend upon the case, right? And the maximum voltage standing wave ratio can be observed. Now this is the case that what we have. Now we have a very simple and interesting equation between ZOC and ZSC. Just you observe them. Prior to that, just recollect what is ZSC. ZSC is equals to ZZ naught tan beta L. That's what we have. ZOC is equals to minus ZZ naught cot beta L. Multiply them. If you are multiplying the open circuit input impedance and short circuit input impedance, ZOC into ZSC is equals to minus J. Just it will be positive. Z naught into Z naught square. And tan beta L into cot beta L, what you get is 1, right? So ZOC into ZSC is equals to Z naught square is an interesting relation that what we have between the open circuit transmission input impedance and short circuit input impedance. So in many times you may get question, they will give ZOC and ZSC, they will ask what is Z naught, or they will give ZSC and Z naught, they will ask what is Z open circuit, the input impedance of the open circuit line. So this is related to the open circuit line and short circuit line. In these two cases we observed zero propagation and the load will entirely reflects the signal. Then if we require a very good signal transmission, or if the signal is to be transmitted through the load, then what is the condition? Now that case is called as matched impedance load. Matched impedance means the load is perfectly matched with the transmission line, that what we are considering. The transmission line characteristic impedance is Z0. The load what I am considering is ZL. If these two are matching, then the maximum propagation must be there. That is our assumption. Now we will observe whether the propagation will be there or not. Now we will observe a very important case of our transmission line. It's a very important transmission line. There is a matched line. So what is a matched line? As I said, if the characteristic impedance of our transmission line Z0 is equals to the load impedance, that the load what we are taking is equals to the Z0, then it is said to be a matched line. Whenever there is a matched line, definitely there must be no reflection, there must be no voltage standing wave, and the input impedance is the thing that what we are supposed to observe. What is Zin? Zin is equals to, write on the basic equation, Z0 into ZL plus ZZ0 tan beta L divided by Z0 plus ZZL tan beta L. Now substitute Z0 is equals to ZL. If you substitute ZL is equals to Z0 and ZL equals to Z0, these two terms will be cancelled. And then Zn is equals to just Z0. So whenever we have a transmission line with load impedance is equals to the characteristic impedance, then the characteristic impedance must be, the input impedance must be equals to the characteristic impedance. That what you can observe, it's a very simple one, right? And clearly it is a pure resistive term. There is no reactance here, right? Similarly, what is gamma? Gamma is equals to ZL minus Z0 divided by ZL plus Z0. Now as ZL is equals to Z0, Z0 minus Z0 always gives you 0. So which is equals to 0. 0 corresponds to no reflection. So gamma equals to 0 for a perfectly matched line is nothing but there is no reflection from the load. If there is no reflection, what happens to that one? The entire signal what we are transmitting or what we are sending in our transmission line will be coupled to the next section. What may be the next section? The next section may be an antenna. The load is nothing but an antenna. The load may be another type of waveguide. The load may be a free space, right? So here clearly, if ZL is equals to Z0, the reflection coefficient is 0, corresponds to there will be no reflection from the output end. And clearly S is equals to 1 plus gamma is 0 divided by 1 minus 0, which is equals to 1. which corresponds to minimum standing wave ratio will be there. Minimum means don't think that existing, but minimum means it is 0, right? There will be no standing wave at all. That the minimum value of our standing wave ratio can be observed here. The minimum value of our propagation constant, reflection coefficient can be observed here, and Zn is equals to Z0. These three are the values for our matched line. Here we observed three different types of lines: a short circuit line, open circuit line, and a matched line. Among these three, we require a matched line for our fruitful propagation. But what is the application of that short circuit line and open circuit line? The application of open circuit and short circuit line is there. If we want a peculiar or particular type of reactance, we can use this transmission line. If you want exclusive capacitive reactance, you can use this. If we want a series combination of L and C, we can use this. A parallel combination of L and C, we can use this one. So the application of our short circuit line and open circuit line will be in taking appropriate reactance. Now we are going to observe that one with the help of another parameter, right? By changing the length of the transmission line, how a particular transmission line will give our required reactance. That's what is our motto. Now we will observe what is the characteristic or how a transmission line will behave if the length is varied. In our previous case, if the load is varied, how it acts, just we observed, right? Now we will observe the transmission lines with different lengths or various lengths. If the length is varying, the electrical length varies, our input impedance will vary. Now we will observe that one for different cases. We will start with a peculiar or a particular length, lambda by 4. So here what I do is, I will consider a length of the transmission line as lambda by 4. Lambda by 4 transmission line. Always remember that the transmission line length will be described in terms of lambdas. A lambda by 4 transmission line, lambda by 2 transmission line, lambda by 8 transmission line. That lambda by 4, lambda by 2, lambda by 8 the word will be described get our length. Similarly, a lambda by 4 dipole, a lambda by 2 dipole, that also will be there in the antenna theory, that a lambda by 2 corresponds to, or a lambda by 4 corresponds to the length of the antenna. Here also a lambda by 4 transmission line, always that lambda by 4 describes the length of the transmission line. So L is equals to lambda by 4, that what I am considering. If L is equals to lambda by 4, then what is the modification or what is the characteristic of that particular transmission line we will observe, right? As L is equals to lambda by 4, what is beta L? Beta into L, that is nothing but beta is 2 pi by lambda into L is nothing but lambda by 4. So just simply what you will get is pi by 2. So whenever the electrical length term beta L is there, you are supposed to substitute pi by 2. Now I will start with the general line. So for the general line, what is input impedance? So Zn is equals to, for a general line, Z0 Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. Here also clearly remember, I am assuming that the line is a lossless line. Then only this equation is applicable, otherwise it is very difficult to solve, right? Now what I do is, I will substitute beta L is equals to pi by 2, which is equals to Z0 ZL plus JZ0 tan pi by 2 divided by Z0 plus JZL tan pi by 2. Don't try to take this as infinity. So tan pi by 2 can be written as sin pi by 2 by cos pi by 2, sin pi by 2 by cos pi by 2, cos pi by 2 comes to this particular term, first term. Here also the cos pi by 2 comes to this first term. So if you observe this one, that cos pi by 2 will becomes 0, right? So the term which is left for us after simplification is Z0 into the first term now becomes 0, JZ0 sin pi by 2 is 1, no problem, directly write down that sin pi by 2 here, divided that the first term now becomes 0, that is the term which is left for us is just JZL. So after simplification of this particular term, what you will get is Z0 into JZ0 divided by JZL. Directly I will write down that one as Z0 into Z0 divided by ZL. Z0 into Z0, JJ will be cancelled, sin pi by 2 is 1, Zn. Zn is equals to Z0 into Z0 by L. That is the equation what you are supposed to remember, but there is a great significance to this particular term. For that what I do is, I try to manipulate this particular equation as Zin divided by Z0, which is equals to Z0 divided by ZL. This Z0 was brought to the left hand side. Then Zin divided by Z0 is equals to Z0 divided by ZL I am writing. Now I will try to manipulate this equation again, or this particular term again. 1 by ZL divided by Z0. Now what is this Zin divided by Z0 and ZL divided by Z0? These two are called as the normalized impedances. So clearly remember this particular point. This will be very much useful to you to understand the concepts in our Smith chart also. Whenever the impedance was divided with its characteristic impedance in the transmission line theory, then it is said to be a normalized impedance. Zin by Z0, normalized input impedance. ZL by Z0, normalized load impedance. Right? So here clearly the normalized term can be represented with a lowercase z in, that a normalized input impedance which is equals to 1 by ZL. So what is 1 by impedance? Admittance, which is nothing but simply YL. So just you imagine what we are doing here. We are considering a transmission line with lambda by 4 length. I am not talking anything about the load, right? Just a transmission line with length lambda by 4 was taken. The length of the transmission line is lambda by 4. I am connecting a general load here. That a general load I am connecting, and the normalized load impedance is ZL. Now what is the input impedance of this transmission line? The input impedance of this transmission line is YL. That the load was transformed as admittance for a lambda by 4 line. Whenever we are considering a load, this load was transformed as admittance to the input end of our lambda by 4 line. That's why it is called as impedance transformer or impedance inverter, that the impedance was inverted here, right? The inverted impedance we are observing. That's why this is also called as impedance inverter. This is for only lambda by 4 line, right? This is applicable for matching purpose. Whenever there is an unmatched section and that unmatched section is to be connected to a normal line, that what we have, if you connect this lambda by 4 line between them, then the unmatched section will be transformed as admittance and that will be matched to the transmission line, maybe with the help of a stub or maybe with the help of another line, right? That's why this is very important and peculiar application in our transmission line, and it is called as an impedance inverter or impedance transformer, and useful for matching application. Here I am taking the general case. If I take open circuit case, if I take short circuit case, just observe. First I will take open circuit case. Now just consider the open circuit case. Z was I am considering for our transmission line. The length is lambda by 4. The electrical length is pi by 2. That's what I am considering. Now observe here. Just the input impedance of our transmission line Zn is equals to, here it is ZOC, open circuit line, which is equals to minus JZ0 cot pi by 2. That's what we have. Now clearly observe input impedance of lambda by 4 line, not exactly pi by 4, it's a pi by 2 line or lambda by 4 line, right? So the input impedance of a lambda by 4 line when it is open circuited is equals to minus JZ0 cot pi by 2. So what is cot pi by 2? Simply it is equals to 0. What you can observe from this particular term? The input impedance is 0. Just you recollect the concept of your circuit theory at resonance for a tank circuit or parallel LC circuit or whatever it may be. Whenever we are observing the impedance as 0, simply that can be replaced with a series combination of or L and C. So whenever there is a series combination of L and C and at resonance, clearly the impedance is 0. That is the point what you are supposed to remember. So now I will do, or I'll try to write down the equivalent of this one. What I am taking? I am taking a transmission line. What is the length of this transmission line? Lambda by 4. Right? A lambda by 4 line transmission was taken. Next, what is the condition we are considering? The condition is open circuit. Output was opened. I am not going to connect anything at the output. Then simply this will be equals to, so what is the equivalent of this one? A series combination of L and C. Just I can replace this one with a series combination of L and C. Why this series combination was observed? Because the impedance at that particular input is 0. As this is 0, I am taking this as series combination of L and C. So whenever a series combination of L and C is required in the circuitry what we have, then easily you can use this lambda by 4 line with the open circuit. So this is for an open circuit line. Now I will go for the similar type of analysis for short circuit line. So for a short circuit line, so what is the input impedance? For a short circuit line, Zn is equals to Jz0 tan beta L. The actual input impedance is Jz0 tan beta L. Now we are supposed to substitute this beta L. Beta L is equals to pi by 2. The electrical length of the transmission line is pi by 2. I am substituting here, which is equals to Jz0 tan pi by 2. Tan pi by 2 is infinity. There is no term to simplify further. So J infinite. Clearly observe here, the input impedance of the transmission line what we are considering is infinity. Now once again you have to recollect the circuit theory that whenever there is a tank circuit and at the resonance, if you are observing it, the impedance is infinite. So clearly a short circuit lambda by 4 line can be replaced with a tank circuit, that is nothing but a parallel LC circuit. So just I will draw the figure again. The transmission line we are considering with length lambda by 4. Now what is the condition for this transmission line? It was short circuited. Whenever it was short circuited, the impedance what we are observing is an infinite impedance. Since the impedance is infinite, clearly this can be replaced with a tank circuit, a parallel LC circuit. So whenever such application is required, a parallel LC application is required, you can take a short circuit transmission line with a peculiar length lambda by 4. So this is a simple analysis of our transmission line for different cases. The length is fixed now as a lambda by 4 transmission line I am considering. If it is general, then it will be used as a transformer or impedance inverter. And if it is open circuited, then simply this can be taken as a series combination of L and C. If it is short circuited, then it is taken as a parallel combination of L and C. So this is a special case, just one case. Similarly, we could go for another case. Say lambda by 2 line, we will observe that lambda by 2 line also. Now the similar type of analysis will be done for length lambda by 2 also. Now what I am doing is I am considering a transmission line with length lambda by 2. I don't want to vary the length. Okay. If L is equals to lambda by 2, then what is the electrical length beta L? Beta L is equals to 2 pi by lambda multiplied with lambda by 2. Just it is pi. So whatever may be the case, I am supposed to substitute beta L is equals to pi. Initially, I will observe that for a general line. For a general line, what is transmission line input impedance? Zn is equals to Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. Now what I have to do is just I have to substitute beta L is equals to pi. If you substitute beta L is equals to pi, what you will get is 0, right? Here also beta L is equals to pi, tan beta L is 0. So these two terms will be vanished, then you will get Z0 into ZL by Z0, Z0 will be cancelled. So Zn is equals to ZL. Now what is this one? We are taking a transmission line with length lambda by 2. We are connecting a load. That load will be as it is appears at the input end of our transmission line. That is ZL is equals to Z in. So this is the parameter or the thing that you can observe for this special case L is equals to lambda by 2. Similarly, observe open circuit line. So for an open circuit line, what is ZOC? ZOC is equals to minus JZ0 cot beta L. Now substitute beta L is equals to pi. So what is cot beta L if you substitute beta L is equals to pi? Infinite. So you will get simply minus J infinity. That the input impedance ZOC of a line, if the length is lambda by 2, you are getting infinite input impedance. If it is infinite impedance, simply as you said in our previous case, this can be replaced with what? Is a parallel or tank circuit, a parallel LC circuit or tank circuit. So just you observe the figure that what I am drawing here. This is a transmission line that what I am considering. A transmission line, and the length of the transmission line is lambda by 2. And what is the condition? Open circuit. The output was completely opened. As it is opened, we are observing the input impedance. The input impedance is infinity. If the input impedance is infinity, simply you can say that this can be replaced with a tank circuit, that the equivalent is a parallel LC circuit. Over. So whenever a parallel LC circuit is required, you can use this one also. In our previous case, a short circuit lambda by 4 line we used for a series, a parallel LC circuit. If you want a parallel LC circuit, you can use that one. Or if you want a parallel LC circuit, you can use this one also, no problem. That's purely depend upon the requirement. Similarly, short circuit line. For a short circuit line, so what is ZSC? ZSC is equals to ZZ naught tan beta L. If you substitute beta L is equals to pi here, what you will get is simply 0. So ZZ naught tan beta L is equals to, or ZSC is equals to 0 corresponds to which type of circuit it is? It is a series LC circuit. So what is the condition we are just observing here? A transmission line with length lambda by 2. I am considering a transmission line with length lambda by 2 and it was shorted with a plate. Then this can be used for obtaining the same effect of our series LC circuit. That clearly a short circuit line or open circuit line in the previous case or in this case, a short circuit line and open circuit line will be useful for observing a series LC or obtaining a series LC circuit or a parallel LC circuit, that's depend upon its length. If you are considering another length lambda by 8 or lambda by 16 or lambda by 32, the characteristics may vary. But this is the procedure for analysis of a particular line. That what we are supposed to do is just you consider the electrical length and appropriately substitute this electrical length in all these equations, then observe it. So how it is behaving, how it is acting. So whenever a line is short circuited, what are the characteristics? Whenever a line is open circuited, what are the characteristics? And if the length is varied for a particular length lambda by 4, a particular length lambda by 2, so how these characteristics will be varied, just you observe, then the analysis of our transmission lines will be finished with this particular topic. Later we can go for the calculation of our transmission line parameters using S parameters, that is the scattering parameters, or using a special chart called as Smith chart, that we can calculate different parameters. So we calculated our input impedance, reflection coefficient, etc. Using our conventional equations. The same parameters can be calculated using a graph, a special graph called as Smith chart. So in our next session we are going to observe what is that chart and how different parameters will be calculated using another parameters called as scattering parameters.